Welcome to Spelling Bee Ninja, where we empower your learning journey with insightful educational content. Subscribe now for free access to a wealth of knowledge designed to enhance your skills. Join our community of curious minds as we explore fascinating topics that will sharpen your intellect and broaden your horizons. Today, we embark on an exciting journey through the world of logical reasoning. As high school students, you stand at the gateway to advanced thinking skills, and understanding logic is pivotal in this process. Logic helps us frame clear arguments and analyze the reasoning behind them. In essence, logical reasoning is the art of using systematic thinking to draw sound conclusions. At the high school level, it's critical to distinguish between two primary forms of logic: formal and informal reasoning. Formal logic relies on strict rules, using symbols and equations to arrive at absolute truths, such as mathematical statements. For example, consider the classic syllogism, "All humans are mortal." Socrates is human. Therefore, Socrates is mortal. Here, if the premises are true, we can be certain the conclusion must also be true. On the other hand, informal reasoning is much more flexible. It deals with everyday situations and does not guarantee absolute outcomes. For instance, an argument like "most birds can fly." Penguins are birds. Therefore, penguins probably can fly lacks the certainty inherent to formal logic, highlighting that arguments based on probability can lead to incorrect conclusions. Advanced logical reasoning requires you to recognize when to apply formal certainty versus informal probability. This distinction is vital, especially since college entrance exams delve deeply into both logic types. Unpacking these concepts not only prepares you for your future academic endeavors but empowers you to navigate everyday arguments effectively. Next, let's consider the fundamental building block of formal logic, the conditional statement, commonly referred to as an if-then statement. In logical terminology, the component P represents the condition, or antecedent, while Q represents the result, or consequent. A nuanced understanding of conditional statements is essential, especially since errors frequently arise from misconceptions associated with them. Take for example the statement, "If it is raining, then the ground is wet." From this alone, one cannot validly deduce that if the ground is wet, then it is raining. Rain is just one of many factors that could cause the ground to be wet. It could also be from a sprinkler or a spilled drink. This misconception is known as affirming the consequent, a formal fallacy we must be careful to avoid. Similarly, we cannot conclude if it is not raining, then the ground is not wet, as the ground could still be wet due to other factors. The only sound conclusion we can derive from a conditional statement like "if P, then Q" is its contrapositive. In this case, it would be "if not Q, then not P." This principle is key to mastering logical reasoning on exams such as the SAT or LSAT. Now, let's explore the significance of necessary and sufficient conditions. Understanding these concepts can immensely enhance your capacity to analyze logical arguments. In our conditional statement "if P, then Q," we recognize that P is sufficient for Q, meaning if the condition P is fulfilled, then result Q must follow. Conversely, we consider Q as a necessary condition for P. For instance, if we say, "If you are a U.S. Senator, P, you must be at least 30 years old, Q," this indicates that being at least 30 years old is necessary to qualify as a senator. However, being 30 years old alone does not guarantee someone is a senator, illustrating the difference between necessary and sufficient conditions. Misunderstanding these terms can lead to flawed reasoning. For example, claiming exercise is necessary for health suggests that it is impossible to be healthy without exercise, whereas claiming exercise is sufficient for health implies that exercising alone ensures good health, which is misleading. Now, let's move to the topic of syllogisms. This three-part logical argument consists of two premises and a conclusion. A classic example is, "All mammals are animals." All dogs are mammals. Therefore, all dogs are animals. Syllogisms can be categorical, dealing with groups and categories, and they come with rules to determine their validity. Though there are 256 variations of categorical syllogisms, only 24 are logically valid. Recognizing invalid forms is crucial for sound reasoning. To illustrate, let's take "No reptiles are warm-blooded." All snakes are reptiles. Therefore, no snakes are warm-blooded. This syllogism seems logically valid at first glance, but it's essential to carefully analyze the premises and ensure there are no fallacious assumptions. This analytical approach is part of developing critical thinking skills. Knowing how to construct and evaluate syllogisms will serve you well in advanced logic. Moving forward, we encounter the fundamental concepts of deductive and inductive reasoning. Deductive reasoning guarantees conclusions derived from premises, whereas inductive reasoning involves drawing conclusions based on observations. For instance, if I observe many swans and conclude all swans must be white, I may be misled, as some swans are black. Therefore, while inductive reasoning can be persuasive, especially when based on extensive observations, it is not foolproof and leaves room for error. Inductive arguments are often impacted by logical fallacies, such as hasty generalization. By understanding inductive reasoning, we prepare ourselves for real-world applications in science, medicine, business, and daily life. Another pertinent example is the red herring and straw man fallacies, common in arguments. A red herring diverts attention from the original argument with irrelevant information. For instance, if someone proposes investing in renewable energy, responding with concerns about job losses in the coal industry detracts from the environmental discussion without adequately addressing it. On the other hand, a straw man fallacy misrepresents an opponent's argument to attack a weaker version of it. This deceptive tactic is often used in political debates, where someone may exaggerate an opponent's stance to undermine their position. Being able to identify these fallacies equips you with the tools to engage in more productive discourse. Furthermore, let's touch on truth tables and logical operators, foundational elements of logical analysis often utilized in computer science and mathematical reasoning. The basic logical operators include and, or, not, and conditionals. Understanding these operators allows you to analyze statements and determine their truth values comprehensively. When creating a truth table, you can see the various outcomes based on different combinations of true and false inputs. This skill is invaluable in various fields, including computer programming and digital circuit design. As you delve into complex logical statements, mastering these operators provides clarity in reasoning. Lastly, we shall explore De Morgan's laws, which elegantly explain how negation interacts with and or statements. Named after the mathematician Augustus De Morgan, these laws clarify how to interpret negated conditions. For example, not P and Q can be expressed as not P or not Q, indicating that if it is false that both P and Q hold, at least one of them must be false. These foundational principles allow for simplification and clarification in reasoning, which is particularly helpful in many applications, including programming and logic proofs. Throughout history, logic has faced paradoxes that challenge our understanding of reasoning itself. Among the notable paradoxes is the liar paradox, encapsulated by the statement, "This statement is false." This self-referential statement raises intriguing questions about truth and falsehood, presenting a contradiction no matter how one interprets it. Similarly, modern variations like the Pinocchio paradox explore the complications of self-reference in language. These paradoxes serve as a reminder of the limitations of formal logic and ignite curiosity about the deeper implications of our reasoning processes. As you navigate the realms of logic, always remember, questioning and critical analysis fortify your understanding and mastery of these concepts. Through logical reasoning, you learn not only to construct sound arguments but also to deconstruct the reasoning of others, unveiling layers of complexity and clarity in discourse. In summary, today's exploration of logical reasoning introduced vital concepts from conditional statements to syllogisms, necessary versus sufficient conditions, and common fallacies that distort arguments. We unpacked essential tools such as truth tables and De Morgan's laws, which are pivotal for mastering logical principles. Through these explorations, you've gained insights into formal and informal reasoning, equipping you with the skills to analyze arguments critically. Remember, logical reasoning is not merely an academic exercise, it's a tool for navigating the complexities of our world. Thank you for joining us on this journey through the intricacies of logical reasoning. We hope today's lesson inspires you to approach arguments with a critical eye and empowers your ability to think logically. Don't forget to subscribe to Spelling Bee Ninja for more engaging educational content. Until next time, keep questioning, keep learning, and stay curious.